Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on February 25th, 2026, just 6 days ago. It introduces the first Tri-Modal masked diffusion model, pre-trained completely from scratch to handle text, images, and audio, achieving strong performance at the 3 billion parameter scale. The paper is titled, The Design Space of Tri-Modal Masked Diffusion Models. And, as we'll see later, the insights into scaling laws and batch size independence suggest a powerful new alternative to standard autoregressive transformers. Well, Figure 1 provides a first look at the model's output quality, demonstrating strong prompt adherence and high-fidelity rendering. It features 4 samples. Starting on the left, Panel A captures natural daylight and depth of field with an egg in a field of crocuses. Next, Panel B details fine fur texture in a black and white lion portrait, while Panel C handles soft lighting. Finally, Panel D depicts a complex multi-object arrangement of noodle soup, which confirms that the discrete diffusion approach works well for detailed visual generation. So, while Figure 1 showed the qualitative results, Figure 3 quantifies the training requirements by plotting the compute optimal frontier. The x-axis tracks total parameters, and the y-axis shows the training tokens. Here, the solid purple line represents the optimal path for the Tri-Modal masked diffusion model, while the gray dashed line marks the standard chinchilla scaling. Crucially, the purple line sits much higher, meaning these diffusion models initially require significantly more data, about 480 billion tokens for a 3 billion parameter model versus just 60 billion for a transformer. However, the slope is flatter, implying that as models get massive, this data hunger grows more slowly. Alright, since Figure 3 defined the data requirements, Figure 2 now details the architecture itself. At the bottom, the diagram displays the input mini-batch, where text, image, and audio are all converted into discrete tokens, yellow for text, blue for images, and green for audio. A mask schedule then corrupts these sequences by randomly replacing tokens with a mask, indicated here by the black crosses. The central gray block represents the bidirectional transformer, which processes this corrupted stream. Ultimately, the top section shows the goal, to reconstruct the original clean tokens, allowing the model to learn relationships across all 3 modalities in a unified way. Okay, having established the architecture in the previous figure, Figure 11 now validates the scaling laws used to optimize it. This scatter plot compares the actual training loss, specifically the evidence lower bound, on the x-axis, against the value predicted by the scaling equation shown at the top. The data points, colored by compute scale, fall almost perfectly on the diagonal line. This tight fit proves that the researchers can accurately forecast the performance of tri-modal models just by choosing the model size and token budget. Well, with the previous figure confirming the scaling predictions, Figure 15 now summarizes the actual capabilities of the unified 3 billion parameter model. On the left, the radar chart splits performance into 3 sectors: green for audio, blue for images, and orange for text, where a larger radius means a better normalized score. The table on the right lists the specific numbers, highlighting solid results like 42% on MMLU. This demonstrates that the model handles these diverse tasks competently, without needing separate specialized networks. So, while the previous figure showed broad performance, Table 1 isolates the impact of a technique called anti-masking. This method trains on both a masked input and its complementary inverse simultaneously. The columns track generation quality using Frechet inception distance for images and Frechet audio distance for audio, where lower values are better. Comparing the base and anti-mask rows reveals consistent gains. Most notably, the audio distance on the Libre speech dataset drops from 0.79 to 0.55, proving that this strategy improves efficiency without increasing training cost. Wrapping up, 2 takeaways stand out. First, discrete diffusion offers a unified, stable alternative to autoregressive models for handling text, images, and audio together. Second, the new stochastic differential equation reparameterization removes the need for complex batch size tuning, significantly simplifying future large-scale training. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.